Hello and welcome to another Zosin session. How about that? So let's do another episode of shader math, shall we? So I think I already did one episode on intersection between circle and rectangle. So I think I can give you the link to that. So basically I've been using fragment shaders and shader toy to explain some mathematical concepts. So maybe for somebody it's going to be interesting as well. Yeah, shader toy math, circle, rectangle, intersection. So here I explained how to detect that your circle intersects with your rectangle. So I'm going to put that link in the description. So previous episode of shader math. So this is probably how we're going to call this series. So, and today I wanted to talk about drawing lines with fragment shaders because it's rather interesting. So fragment shaders are like basically shift your paradigm of thinking about computer graphics, right? Usually when you have a graphics library or graphics framework, I'm gonna sneeze just a second. Excuse me. So usually when you have a graphics library or graphics framework, right, so you issue commands very explicitly, right? So you want to draw a segment or line, you say, here's the point P1 and here's the point P2, draw the line between them, and the library goes ahead and just draws this entire thing for you on the canvas of some sort. So this is not the case with the fragment shaders, right? Fragment shader is essentially a function, right? It's a function that accepts a coordinate of a single pixel, right? So something like X and Y, or maybe like U and V or whatever, right? And outputs the color of the pixel, and that's the only thing you're allowed to implement. Right, so you have to implement a single function that accepts coordinates of the pixel, and based on the coordinates of the pixel and maybe some global variables, right? Maybe there's some global variables that we call uniforms in the industry. I think they're called uniforms, and based on that it will compute a single pixel, right? And since all of that is run on the GPU is capable of running so many of such functions in parallel. The the speed is phenomenal, right? So and that kind of shifts completely the paradigm of thinking about computer graphics. And the question is, how can you even draw a line if you're only allowed to, implement like a function that colors a single pixel? So how can you do that? So let's actually take a look at how the fragment shaders looks like. I have OpenGL template in here. So it's just like a simple template application that I wrote in C, and basically it does all of the like boilerplate, like the usual OpenGL boilerplate. A lot of people who work with OpenGL, they do have this kind of a template, and I use it for like to quickly set up OpenGL stuff. Usually I wanted to usually use a shader toy for this kind of explanations, but I don't really like the shader toy UI, you know? I don't really like it. So, and the editor is kind of crappy, especially if you got used to these unusual editors like Emacs and Vim. I just like don't like the key bindings and stuff like that. It's just like, nah. I rather have my own thing, right? So, and in my own thing, I can open the shaders, right? So I can open the shaders like so. So, and let's run the application. So maybe I can split the screen like in half, right? And I can edit things, right? So for instance, I want to make the whole thing black, right? So I'm going to do vector 4, 0, and I'm going to reload, and everything, as you can see, is black, right? So now we may try to do something. So if you want to render a circle, we actually render the circle several times on the stream. Essentially, you need to decide what's going to be the center of the circle, right? And knowing the coordinates of each individual pixel, you can test the distance between those coordinates and the center, right? And if it's close enough, you color it one color. If it's not close enough, you color it a different color, and this is how you get a circle, right? So if I put the center of the circle somewhere, I don't know, at 200, right? right? And then I take the coordinates of the fragment. So I have already coordinates in here which are normalized from 0 to 1. I don't really think I need that in here, so I'm going to actually take not normalized one. And I'm going to compute the distance between the center and the current coordinates of the pixel, like this. And if this entire thing is less than a radius of the circle, we're going to be setting the color to, let's say, white, right? Otherwise, we're setting the color to black. And that's basically how you draw the circle, right? So we probably need to define the radius somewhere. So we already have a radius of some sort in here. I'm not really sure what the hell is that, but I'm going to define my own one. So let's say the radius is going to be 100, right? And if I refresh, there you go, here is the circle, right? So this is, I suppose, 200, 200, and you know, we run this function simultaneously for each individual pixel, and it computed the circle. So instead of the specific center, we can try to use the mouse, right? So now it's actually attached to the mouse, right? And the mouse position is actually passed, you know, from the CPU to GPU via the uniforms. So here we have, you know, an access to the mouse and to the resolution of the screen, and we also have access to the time, right? We also have access to the time, and time is usually used in shaders to to do some sort of animations, right? For instance, I can take like a sine of time, and I can get a value from -1 to 1, oscillating over time, right? But it's not particularly convenient to have it from -1 to 1, so it would be better to normalize it to 0 to 1, right? So, and to do that, we can multiply this, actually we can add 1, so now it's going to be from 0 to 2, right? And then we can divide it by 2, right? There we go. So we have a value that is oscillating from 0 to 1, and we can essentially multiply a radius by that value, and that will create an interesting effect of a circle actually expanding and shrinking over time. So, and yeah, so that's basically what you can do with the fragment shaders. But the question is, all of that is relatively straightforward, and all of that is relatively simple. But how the hell do you draw a line in that particular case, right? How do you draw a line? That's a very interesting question. So, essentially, imagine that you have, I'm going to show how I usually do that, right? So there's probably a lot of different ways of doing that because math is so versatile. So I'm going to have like 2 points, right? So in our shader, we're going to be defining 2 points. And essentially, what we need to do a similar thing as with the circle, right? In the circle, we check how close are we to the center of the circle, and if we closer than the radius, we have to color it in a particular way, right? So we can do a similar thing. We can pick a point, right? Because we're going to be knowing this point because the function is called for all of the points simultaneously to some extent. So we need to find the distance, the shortest distance between this point and the segment, right? So you may say that it's some sort of like a normal, right? Because it's going to be 90 degrees or something. So we're going to take this distance, and if the distance is less or equal than the thickness of the line that you want, you also will have to define the thickness of the line, right? So maybe you want it to be super thick, right? Or maybe it's going to be like 1 pixel or less than a pixel. Maybe you're going to have like a sub-pixel situation, right? And if it's closer than the thickness, you want to color it one color, otherwise you want to use the background color. So, and that's basically the idea in here. And you also need to consider the situation when you're outside of the segment. If you want to draw a segment, if you don't care whether you draw in segment or not, you want to just the whole line, you don't care about that. So the question is, how do you even do that, right? How do you even do that? So I'm not really good at math. I was terrible at math in school, and I think I'm still terrible at math. So I had to sort of reinvent this way myself. So essentially, we can probably employ something that is called dot product, right? So an interesting thing about the dot product of 2 vectors. So let's actually take a look at it. Dot product. It's a very simple operation. It's a very simple operation on one or two vectors, which basically compresses them into a single value. So I think I'm going to put the dot product link in the description, right? So dot product, and I think I forgot to give you the link to the source code of my OpenGL application that I'm using in here. So let me quickly do that. So it's located at Sodic OpenGL template. There we go. Sodic OpenGL template, if you want to use it. I'm not sure if you want to use it. Usually people just implement their own thing, but in case you want to use it, here it is, OpenGL template. There we go. So dot product, as you can see, it's pretty straightforward, right? So essentially it's a sum of the products of each individual component of the vector, right? So if you have two vectors, for instance, let me actually write it properly, A and a B, right? And you do a dot product between them. Essentially what you're doing, you're taking x of A, multiply it by x of B, and then add y of A multiplied by y of B. So that's how you compute that. So that's basically the action that you will have to perform to compute the dot product between these two vectors. But it doesn't really tell you much, like why the hell would you even do that, right? So what's the point of this like magical operation? Well, it has a different formula that you can use to compute it. It's this one, right? You see, by doing that magical operation of just multiplying the corresponding components of the vectors and summing them up, you're also computing this thing, basically a product of the length of A, length of B, and cosine of the angle between those things. So let's actually see, like imagine that I have, so this is going to be A, right? This is a vector A, and this is going to be a vector B. Right, and there is some sort of angle alpha between them. So the meaning of this operation is essentially multiplying the length of A, the length of B, right, and the cosine between them. So think about it this way. You perform this operation, but in reality you're computing that. But you don't really get each individual component in here. So you get this information sort of packed into a product, right? So if, for instance, you want to extract alpha, then you will have to unpack that alpha. You will have to divide it by the length of A, divided by the length of B, then you will have a cosine of alpha, and then you will try to take the arc cosine, like anti-cosine, I don't know how it's called in English, I'm sorry, right? So to get the alpha, but usually you don't really need to do that. So essentially you perform this operation, but you get this information that you can then use to do some other things, right? So, and let's imagine that we have a P1 and P2, and there is a P3, right? So we can treat this sort of situation as two vectors, the vector P1, P2 and P1, P3, right? So, and we do know the length of P1 and P2 and the length of P1 and P3. And by doing a dot product between these two vectors, we can find the cosine of the angle between them, right? So essentially, yeah, let's do P1, P2, vector product between P1 and P3. And that essentially gives us the length P1, P2 multiplied by P1, P3, something like that, right? And multiplied by cosine of alpha. So okay, cool. We've got the cosine of the angle between these two vectors, but what kind of information does it give us? Okay, so to understand what kind of information cosine of alpha gives us, we need to understand what the hell is cosine and sine, essentially, right? So I think the naming that people gave to concept of sine and cosine are kind of confusing because it sort of hides the like actual real useful application for them. but it's just my opinion. So I'm not even a mathematician, so what do I know about this kind of stuff? So let's actually take a look at the trigonometrical circle, right? So imagine that you have a circle of radius 1. Right, it's a circle of the radius 1, so these two things are going to be essentially 1 and 1, right? And imagine that you have some sort of an angle, right, alpha. So essentially cosine of alpha is this point of this vector of length 1 projected on x. And sine is essentially the same thing but projected on y, right? So essentially cosine and sine are x and y coordinates of the vector of length 1 with the angle alpha. That's what they are. Right, so effectively for all practical means and purposes, cosine is basically x of vector of length 1 and sine is basically y of the vector of length 1. Seriously, like there's maybe more to that, but usually when you use cosine and sine in practice, that's what it means. They are just the coordinates of a vector of the length 1. Right, and here's an interesting thing. What if this vector was length not 1, but for instance 2? When you project it in here, the value of x of that thing is going to be cosine of 2. And the same will go for y. It's going to be sine alpha of 2. Right, so basically, it essentially cosine of alpha projects itself to this sort of vector, right? So, and that's effectively what we can use in here, right? Cosine of alpha in this particular case is going to be basically basically the length of P1, P3 multiplied by cosine of alpha in here. You see? So if the length of this vector was 1, the length of this thing would be cosine of alpha. But since the length of this vector is this, right, this, you multiply cosine of alpha by this and you get this thing. So now you know the length of this thing, which is already pretty cool. Look, look, look. Now already you know the length of this thing, and since you know the length of these things, you can find precise coordinates of that thing, precise coordinates, and now you can compute the length of this thing. And once you know the length of these things, you're pretty much good to go, right? So you can just compare it with the thickness of the line, and that's how you draw that. That's essentially how we draw it. It's as simple as that. So you just need to get that cosine of alpha, and that will basically give you the projection in here. Hopefully that makes sense. So let's, I suppose, go ahead and code that in a shader in some particular sense. But maybe before we go ahead and code that in a shader, I want to make a small break and I want to refill my cup of tea because I've been explaining things a lot. So I need to refresh my cup of tea. So, all right, let's go ahead and code that. So where is my trusty editor? Here it is. So first of all, I'd probably like to extract the function that draws the circle into something, right? So because we're going to be using circles as sort of markers on the screen, I think it's going to be super convenient. So let's actually literally call it like marker, right? And I'm just thinking, so I don't know, maybe, oh yeah, we have an access to the colors, so we don't really have to do anything. So we only need to have an access to this x and y. But we still also have it because input and output are both global variables, so we don't really have to do anything in here. So let's accept the center of the marker, right? So this is going to be the center. And in here, we're going to be extracting this entire thing like that. Right, and on top of that, I think it would be nice to have some sort of a color, right? Vec for color, right? And if the length is less than a particular radius, so in that case, let's say that we're going to have a special radius for the markers. Marker radius, and it's going to be equal to something like marker radius. Let's say it's going to be like 50. We can always adjust that. So, and if it is true, to the output color, we're going to be adding the color over the marker. Right, and the else in that case is not really needed because we're, oh my, so the output color is called color and the input color of this function also called color, so we have to think about a different name for these things, I suppose. I think it would make sense to call this something like out color, right, because it's the output of the fragment shader, and let's rename it like this. Okay, so here's the function. Also, let's actually go to the entire code base and just remove the useless crap. So R and radius are not needed anymore. We have a marker radius only. We don't need to normalize the coordinates, the screen coordinates and the mouse coordinates. It's not needed. So, and in here we're finding some stuff which is not really that important anymore. So here is the center, and I'm pretty sure like I can remove all of that. So now I can say marker mouse, draw a marker at the position of the mouse with the color red, right? So that's basically what we're doing in here. So we're gonna have a marker, a special marker in here, and something went horribly wrong. I don't know what the hell just happened. But maybe this is because we never actually clean the out marker. As you can see, like maybe it just contains a garbage. So let's go ahead and just clean the entire thing. Is that the case? Yeah, it was the case. I didn't know that. Oh my god, I just learned something. Apparently, by default, actually I can still see this thing in my eyes. Working with the graphics API is actually dangerous. So I guess we're gonna have some sort of like an epilepsy warning or something, right? It's kind of interesting, like working directly with graphics APIs is dangerous for your eyes, and working directly with sound APIs is very dangerous for your ears, because if you also screw up, you may end up with a very loud sound, which can damage your ears, right? Especially if you're using headphones and stuff like that. So I guess it's the same for graphics. Game engine development is a very dangerous job apparently, right? So it's very interesting, actually. Never thought about it. Anyway, so we have a marker. I think marker is too big. Let's actually cut it in half. Right, so maybe I would even cut it further. Right, so I think... so not 25. What I wanted in here is... oh my, so it's basically this. That's what I wanted. That's what I was thinking about. Okay, so here's the marker. And let's also define some place where the line starts. Okay, so as we already said, we have basically 3 points, P1, P2, and P3. Right, so let's actually define them explicitly. So in our case, P1 is going to be some fixed place on the screen. So let's say it's going to be 200 by 200 as we did initially. Right, the P2 is going to be mouse, right? So P1 is fixed and P2 is mouse, and we can control the position of this entire thing. And P3 is essentially the current pixel on the screen. So it's going to be glfrag xy. So there we go. We have 3 points, P1, P2, and P3, as we talked about in here. So let's actually put some markers on these 2 initial points of the segment, right? So this one is going to be P1, so we're going to color it red, and maybe P2 is also going to be red. So basically they are the ends of the segment that we're trying to draw, right? And something went wrong, and I think usually that happens when there is some sort of a compilation error. So initializer vec2 cannot be assigned to variable vector3. Oh yeah, I made a typo in here, so just a second, it's going to be something like this. And there we go. So now, as you can see, we have 2 points in here. One is fixed and another one is you know, attached to the mouse, which is rather convenient. Okay, so now what we need to do, we need to find a dot product between vectors p1, 2 and p1, p3. Right, so as far as I know, GLSL has a function for dot product, GLSL dot. Let's actually find that function. So it accepts these two vectors and return you the value. Okay, so let's do something like this. This is going to be dot, and it's going to be dot between p2 p1, right, and the p3 p1, right, p3 p1. If we take a look at this thing, like p2 p1 p2 and p3. Cool. Maybe we could also extract these values into their own separate vectors, something like vector p12, which is essentially this p12, right, and the vector p13, which is essentially this, right, p13. There we go. We found the dot product, and that dot product is basically equal to the length of this thing multiplied by the length of these things multiplied by the cosine between those two vectors, right? So let's actually do it like this. Equal length of p12 multiplied by length of p13 multiplied by cosine of angle between those things. So we don't really care. We don't really care about this aspect of this product, right? Because the only component we care about is p1, p3 multiplied by cosine alpha. So that means we need to take this dot product and divide by the length of p1, p2 to sort of get rid of it from the product. So as already said, when you do dot product, you get some useful values packed, encoded, and you basically need to clean up the garbage, right? So in this case, the garbage is going to be the length of this vector, so let's actually clean it up. So we'll have to divide this entire stuff by the length of p12, and this entire thing becomes equal to just this, and that's the length of the of this vector. So this is the length of this specific vector. So okay, how can we call that? We can just call it d, right? We can just call it d. So, and now once we have the length of that vector, we can try to find the point, the projected point on this thing. So we need to find that stuff. So maybe I should start using different color. We need to find this thing. Let me find something like this. Yeah, we need to find that. So to find that, I'll need to take the vector p12 and probably normalize it, right? So I need to make its length equal to 1. Yeah, we do have a normalizing here. And then once I normalize it, I can multiply by the length of that projected vector, and I get, you know, essentially 0.4. We can call that a point 0.4. Right, and after that, we can find the length of this entire thing. It's going to be 0.4, just a second, 0.4 minus 0.3, and the length. And now, if this entire thing is less than the thickness of the line that you want to draw, you're going to be setting the color to the color of the line. So in that case, let's actually say that it's going to be green, right? So 1, 0, 1, there we go. Maybe alpha doesn't really matter in this case. I don't remember. I think I do handle alpha in here. So let's just oversaturate it in here, whatever. Okay, so that should be it. And if I, yeah, so it actually didn't compile because we didn't define thickness. Okay. So let's define the thickness. How thick do I want my line to be? Let's say that is going to be like 10 pixels. My God, somebody's sending me messages. What the hell is going on? I'm in the middle of trying to educate people. Okay, so let me see. So now it seems to be working. It still does not. Let me see what's going on. So color. Oh yeah. So it's now called color out, right? It's now called out color, not color out. But yeah, there we go. Still no. Initialize a vector can be based on variable float. Okay. So where is the float? Yeah, so vector. Okay. Now, and it doesn't work. So let's try to understand why. Let's try to understand why. That is very, very strange. So It should work according to my calculations, though, at least. Well, probably this is because I actually take a normalized vector p1, p2, but it's actually attached to the 0, so I have to offset it to p1. Okay, so yeah, so this is the mistake, right? So I need to offset it to p1. And now we have a line. Isn't that cool? Yeah, so, and you can control the thickness of that line however you want. Right, so let's actually make it like 5. Right, it's going to be less thick. And maybe you want to make it super thick, like 50. Now it's super thick. As you can see, by the way, it's not anti-aliased, so you can see these staircases and stuff like that. So we already talked about anti-aliasing on this channel. And we even implemented like a simple anti-aliasing for circles, right? So I think you can find a video where I talked about anti-aliasing in here somewhere. So Tsodin Daily, let me find that. Tsodin Daily. So anti-aliasing in Rust. So if you're interested in this kind of thing, I'm gonna redirect you there. Let me find the description. So this is gonna be where is description? Okay, so what is going on? Okay, what do I want? Emacs locked by that is sus. Why is it locked? I didn't lock this entire thing. How did I lock that? Okay, so apparently I don't know, but I need to add that to the description, and for some reason I cannot do that because the file with the description is locked for whatever reason. What is going on? Okay, so maybe I'm gonna actually add the description to... What the hell is going on today? I'm just trying to record the video and everything is going wrong. In the middle of me trying to record the video. I'm really apologize for that, but anyway. So, so anti-aliasing, right? So we need to implement some sort of anti-aliasing because this looks like shit. That's what I wanted to say. Right, and the way you do that is just basically you start doing subpixel computations, right? So basically all of the computations here we're doing on the level of each individual pixel, right? So we're basically limited by the resolution of the pixel itself. But if we do the computations on a subpixel level and then sort of merge our computations into a single pixel by adjusting alpha or some sort of blending, it may become like a little bit smoother. And for more information, look at the video in the description. Yeah. So apparently, like I recently learned that this kind of technique is actually called multi-sampling. I didn't know that. I know nothing about OpenGL, so I don't know its terminology. But apparently it is called multi-sampling. So multi-sampling. If you Google it up, yeah, so it's OpenGL thingy. And you can actually enable multi-sampling and ask OpenGL do this kind of stuff for you. Right, so let me see how we can do that. I think it depends on what kind of window API you're using, right? So I think you need to specifically say GLFW. In this particular template, we're using GLFW. Enable multi-sampling, right? So you know what? I think I'm not going to read documentation. I'm going to just straight up read the source code. GLFW. Right, multi-sampling, sampling, because I do remember that SDL had a support for multi-sampling, right? But I'm not sure if GLFW does support for that. So multi-sampling, or maybe it's a, oh, maybe it's an OpenGL thing. Okay, so it's probably OpenGL thing. I'm sorry, I don't know, I had a brain fart. Multi-sampling enable, right? So let's see, I think you just have to do GL enable, Yeah, sample alpha to coverage, enable line smooth. I don't remember. Still OpenGL multi-sampling. Why am brain farting multi-sampling SDL? Right. Am I going crazy because I remember doing that? Yes, so you do that through the set attribute of SDL. So, okay, cool. Multi-sampling, but is there something like that for GLFW? So that's the question. Apparently, it's a purely SDL thing. Okay. Maybe there's no way for us to do that in GLFW. Don't forget to use GL multi-sample. Okay, maybe you can just go ahead and stack it into your thing in here. So let me see, main.c. So here we are creating the context, and maybe after we created the context, I'm gonna do GL multi-sample. Right, and let's recompile the entire thing. And there we go. Did it help? It didn't help. Okay, so that's cool. I don't know, maybe it doesn't really matter that much. In SDL, it's super easy to enable it. In GLFW, I probably have to read more into the documentation, but I'm too lazy to do it right now. Anyway, so here's the thing. So we're drawing like the whole line, right? We're drawing the whole line. But how do you draw a single segment? Right. So you need to also have additional condition that checks that you're not outside of that specific segment. So how can you do that? Let's actually go back to the drawing board. Let's go back to the drawing board and let me see. So if I understand correctly, the logic of checking that you're within the circle should be relatively straightforward. So this is a P1, P2, and in our case, the point here is called P4 because the P3 is the point against which we're checking this entire stuff. So that's why it's P4. Right, so essentially, the interesting part, this interesting condition of this point is that if it's within this segment, if I understand correctly, we will have to test that. If it's within the point, the length of P1, P4, right, is going to be less or equal to the length of P1, P2, right? So the length of this thing is going to be less than the length of this thing, right? Makes sense. And another thing is that the length of this thing is going to be less than this thing, the whole thing, right? So P1, P4, right, is less or equal P1, P2. There we go. So if at any point this thing is going to be here, its length may become so between its length between P4 and yeah, I just realized that it has to be 2. All right. So P1, P4 is less than that, and P2, P4 is also less than that. Right. If at any point this point goes outside of this segment, right, it goes outside of the thing, one of these conditions may become false. Right. And this is basically what we want to try to exploit here. Right. So let's actually go ahead and put that in the code and see if it's going to work. Neighbors are trying to do something fishy yet again. Oh my god. All right, so fragment. Let's see what we can put in here. All right, so the thickness is right, and then the length of P4 minus P1 is less than the length of P12, and the length of P4 minus P2 is less than length of P12. So less or equal, right? Less or equal. So we're effectively sort of clamping this entire thing, and let's see if it's going to work. I'm not sure if it's going to work. So let's actually put this stuff like that, so it looks a little bit better. We can see all of the conditions. So first we check the thickness, right, then we check the rest of the stuff. Okay, so, and there we go. So we clamped the entire segment. So now we're drawing this specific segment. Okay, and we can decrease this thickness to, I don't know, 10, because I think it's too thick, right? So now we have a line. Yep. It would be nice to enable multi-sampling, but I have no idea how to do that in GLFW. Right now, I can just go into documentation and read about that, but I'm just too lazy to do it right now. So, and I don't really care about it right now. It would be cool, but it doesn't really matter that much. So, yeah. So I would like to share this shader with all of you. So, and the easiest way to share the shader would be to probably port it to ShaderToy. So let's actually go to ShaderToy and see how we can easily port that. ShaderToy new. So there we go. ShaderToy new. So ShaderToy has a slightly different interface. As you can see, it passes the GL fragment color and like fragment coordinates via the arguments of these functions. So yeah, we'll have to probably adapt all of that. Also, you see, we have a special function for the marker, right? So we have a special function for the marker. Maybe I'm going to extract that like line also into its own separate function that accepts 2 points and the color and just encapsulates this entire process. I think that will be actually kind of cool. So let's go ahead and do that. So this is going to be line, and we accept vector 2 p2 and vector 4 color, right? And let's extract all of that stuff in here. So this is going to be that. So P3, and I guess that is it. I'm pretty sure. And that will enable us to do something like line P1, P2, and the vector 4. And let's give it the color blue to confirm that something has changed. If it's going to be still colored with color green, we won't ever know that it, you know, something changed, right, at all. So yep. So, and now we have like very convenient functions that do kind of resemble the, you know, the non-GPU way of doing computer graphics, right? Where I can say draw a line, then draw a marker, and draw another marker. It sort of like feels like an imperative way of programming, even though it's more of a declarative one, right? So we basically rise the level of abstraction, and now we're issuing imperative commands in here, which is kind of cool, I think. So yeah, you can basically jump back and forth between the paradigms. So yep. So it seems to be, let me actually, so exited abnormally. I don't know why it exited abnormally, but okay. So let's compile everything, and something, yeah, as you can see, something doesn't really work well, right? Even though, oh yeah, that's precisely why I use the different color, right? So if you're making some sort of refactoring, right, try to make some also small changes that also slightly change the behavior, so you can confirm that the refactoring didn't break something and you did it correctly. For instance, here I forgot to change the color, and if I didn't try to use a different color here, I would probably never caught that. So that's a pretty interesting lesson. It's a pretty good lesson. Okay, there we go. Now it works. So it's pretty cool. Okay, why when I press Q it exits abnormally with exit code 1? That's really sus. Let me go in here, so let me find Q. 2. Is that because I explicitly keyboard? Yeah, because I explicitly say exit with 1. I have no idea why. And I'm pretty sure this is not the correct way of exiting GLFW. I think the correct way of exiting GLFW is GLFW set window close or something. I do remember something like that. Set window should, yeah, set window should close, that one. Right, so you take this thing and just do it like that. So because you do have an access to a window, right? And then we can set the value to 1, right? And there we go. And we don't have to do exit in here, because then on the next iteration of event loop, this condition will become true, false, I mean, and will exit gracefully. So we don't really need this kind of stuff anymore. So that's a little better, and we're exiting with a 0 exit code properly. All right. So again, let's go back to porting this entire stuff to to shader type. Okay, so obviously it's not gonna work right away, so let's put this kind of stuff. Let's be a little bit more careful. Okay, so I'm gonna just copy paste it like that. So we don't need to specify any precisions. Can I make the editor a little bit bigger? I think I can. Right, so we don't need to specify this stuff. A resolution is not important, time is not important, mouse is done completely differently. This is not important. Okay, so when we set the marker, we need to know the frag coordinates. Unfortunately, we don't have an access to these kind of things globally. Right, so they're not globally available, unfortunately. So I wonder if we'll have to pass this kind of stuff around. The last time I tried to do this kind of thing, it actually didn't work for whatever reason. So I suppose this is what we can do, right? So we say that the output is a fragment color, and the input is a fragment coordinates, and then the rest of the stuff. It would be way more like readable if it was like a global stuff, because I mean we're not developing such a huge program where global variables become a problem, right? So it's kind of pointless in my opinion, but it is what it is. We have no choice in here, right? So basically I want to be able to freely share my shaders, and FaderToy provides this opportunity for me, and I'll have to put up with whatever shenanigans they want, right? Even though if they force me to write the code in an inconvenient way, well, that's the price to pay for sharing the shader, right? That's the price you have to pay. It is what it is, and it isn't what it isn't. Is it not? I think it is. The missile knows where it is because it knows where it isn't. Let's actually continue. So this is going to fragment coordinate x, y, and the output is going to be something like frag color. Right, there we go. Okay, I think I did everything correctly. So this is the input, and maybe I can also mark these things as an input, right? So, and suppose input and output qualifiers are like similar to like C# ones, even though I never programmed in C#, but I heard that C# does have them. And I programmed in Ada that also has a similar qualifiers, so I do kind of understand what they mean. Okay, so this is going to be that, and just for the sake of consistency, right? Consistent code is readable code. No matter what your conventions are, if they are consistent, it actually helps in reading your code, because it just like sets up the expectations, and yeah, you don't have to worry about explaining the same thing over and over again in your code. Right, so out color is frag color, there we go. So, and essentially this thing becomes the new main, right? This entire thing becomes the new main, so I'm gonna just remove the entire thing. And then I'm going to just put it in here. So the output color, I suppose, is going to be frag color. There we go. So this is a frag color. So then we set some sort of position. Mouse in terms of shader toy, I think it's I mouse, X, Y. And then we set the rest of the stuff. And in here we'll have to provide frag color, frag chord. Right, and as you can see, this is the result of these things not being global variables, right? So you have to add, like, you have to pass them along, and I have no idea if it's gonna work at all, because the last time I tried to do something like that, it didn't really work for whatever reason. I don't remember why. So maybe all of that stuff that I'm doing in here is absolutely useless. We'll see. Okay, so let me see. And did it compile? It didn't compile because this thing, yeah. So this function. Yeah, I forgot to remove that. So I needed to remove this entire stuff. Already has a body. What? Okay, cool. And as you can see, it didn't work for whatever reason, even though I kind of like cleaned up GL color, it still doesn't work. I don't really know why. Don't really know why. So, yeah. So this is a frag color, and everywhere here I'm actually passing it as an output parameter. So you can still see this kind of thing, right? So it just moves this stuff around, but it's absolute garbage. And this is what I was talking about. The last time I tried to like organize this kind of stuff in Shader Toy, it didn't really work properly. And that's why I didn't want to use it for explanations, because yeah, my code is way more readable, right? It's just like, it's so straightforward. It uses yucky global variables. I do understand that it's bad and all, but for some specific situations, it's fine and produces readable code. But here, I don't know, it would be way better if all of that was just global. iMouse is global, for instance, for whatever reason. Resolution is global, but this is because they're uniforms. But I mean, Shader Toy developers could have made them parameters of this function as well. I don't know. It is what it is, and it isn't what it isn't. So, and I don't really know what the hell is going on. Because I would expect the frag color to be passed by a reference, but yeah. So one of the things we can do essentially is just don't care, I suppose, and for each individual marker in here. All right, so I'm just gonna copy paste it like that. So the first thing is the center, right? So it's gonna be P1. So this is the first thing, and then the second thing is gonna be P2. There we go. Here is your second thing, and for the line we can copy this kind of stuff back. Like really, I don't really know why it doesn't work. And produces the garbage. Maybe somebody in the comment section can explain me, but it's really counterintuitive to me, and I would rather prefer like this sort of separation into the commands, but this is not something that I can easily do with Shader Toy. So, and a frag color to the 2. So, and that's the color. Okay, so it's gonna be vector 4, red. 1. Okay, so oh my god, it's so the editor is so bad, my god. Okay, so this one has to be okay, so let's actually set it to I don't know, green. Let's put it to the green this time, and now it works. So yeah, even though I marked all of these parameters as out as well, and if something is out, I would expect it to be passed by a reference, but apparently it's not the case for GLSL. I have no idea why. So, but yeah, if you want to play with the thing that we developed on today's stream, here it is. I'm gonna put the link to this specific shader toy in the description. So yeah, here is my thing, which is super straightforward, and here is the shader toy adaptation, right? So here's the shader toy adaptation, which kind of forced me to merge everything together. But again, I don't know with GLSL, maybe I'm doing something wrong. It's kind of shorter, sure, it's kind of shorter, but maybe, I don't know, whatever. All of that doesn't matter. All of that is just styling or whatnot. Okay, I guess that's everything that I wanted to say today to you. So let's take a look at the final result, and boom. So yeah, you can draw lines in Fragment Shaders. Wait a second, I just had an idea. Who said that the thickness has to be regular, if you know what I'm talking about? Who said that it has to be regular? So what if I say thickness, but thickness multiplied by sine of time? Okay, that's very interesting. So let's actually implement the function sine 0, 1. So it's going to accept x, all right, and 1, 2, 3, 4. And so essentially we return sine of x, it's -1 and 1, plus 1, it's 0 to 2, and then we are multiplying this entire thing by actually dividing by 2, right? So let's divide it by 2. Okay, so, and did it work? It did not work because I think it's I time, right? Yeah. Oh, because I paused it. Okay, so yeah, there we go. So it actually changes over time, which is kind of cool. Look at that. Yeah, you can change, but that's not it. Who said that you have to change it over time? You can try to change it based on the length between P3 and P2. Yeah. So, we can shift this kind of stuff to the length of P1 and P2. And that kind of creates a very strange situation. So it actually creates 3 of them, which I do not fully understand. Like what I wanted to create is I actually make it like a little bit more wobbly, if you know what I'm talking about. So so the thickness is that. So, and we have set the time by the length of P. It's not P4, P3. I think it has to be P1. There we go. That's what I wanted. That's what I freaking wanted. Look at that. So there, it's now wavy, and maybe we can even change the, like make it a little bit more spread or something. Let's actually multiply it by half. If I multiply, yeah, you can control this shit. Holy fuck. Wait a second. Oh shit, I started to do some shit. Yeah, look at that. That is so cool. And it just moves over time. And I suppose maybe we could multiply time by 2 so it moves a bit faster. All right, so yeah, you can do this kind of shit. Holy fuck, that's cool. So if I make the thickness like 50, right, so now it's that. That's cool. Yeah, you can play with that idea as much as you want. It's just so really cool. So, and you can make it spread even more. Oh fuck, this is so cool. So what if we remove the clamping between those things, right? If you know what I'm talking about. So what if we don't clamp in here? All right, so this is gonna be something like that. And holy shit. Well, it would be, yeah, this is because of how we check for this stuff. Yeah. But that's cool. That's really cool. Yeah, you can get this idea to a pretty cool state. Oh, this is so nice. I love that. So yeah. Yeah, you can find the link to this thing in the description if you're interested. I'm gonna save that as well. So okay. This is the shit that makes me happy, like discovering these kind of things. All right, so it's pretty cool. That's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you in the next video. Love you all.